Okay, today we are going to design the second project, which is actually the tents and trees. So the tents and trees is a puzzle, and the definition is already given in the second project. And now we will solve the problem by using a similar strategy as we have given in the book, in the Dart example. Okay, so let's start the design. Before actually starting the design, we will first copy and paste the Q data structure because we will utilize the Q data structure. In this case, we can utilize either the array Q structure or the linked list Q structure, whichever is possible. Let's try the array Q structure. Let's copy and paste it in our main. So this will be added to the operation. As we see, we also need the element. So let's copy and paste also the element to the package. So then you see the element here is actually an integer, which will not be actually an integer because we will actually utilize the in the project the state. So in order to solve the project, we need to have a state representation. So in the state representation, we need to represent a possible solution, sub-solution of the puzzle. So similar to the Dart game problem, let's define a class as state. And then in the state, what will be stored. So a state of a solution is actually a state of the grid. So because we want to put the tent next to the trees, and a possible representation of the grid is actually a type of, let's say, a representation and double array actually. So in that case, we also need to what will be an element to the grid. So we can either do something like the array, integer array, which is possible. We can also do something like an enumerated class, and in the enumerated class, we can say, okay, so let's say it is an item or it is anything, and the item could be a tent or a tree or empty. So in the beginning, since it will be an empty, we should place the empty here. Maybe then the tree is the second and the tent is the third. So in that case, we can do this as item grid. So it should be also a private member. So this is actually the a state representation. And also we need to actually, if we want, we can, let's say, show how the solution is constructed, but for the sake of simplicity, we will not do that. And we also need actually a constructor for the state, which actually needs to read the state, the starting state from the file. So let's write a constructor which actually needs to read state from the file. So let's give a name. So let's say we have a file name and it will construct the grid. And in that case, we also need to read the file and the details will be implemented. Let's say, let's give the details. So the input file name where the initial puzzle is stored, let's say. And then we will read the puzzle from the file and construct the initial state. So we can have a state And then what can we do? We can, for example, print the state, etc. But we will see that later. So other than that, we will also solve the puzzle. So how will we solve the puzzle? In the state, we need to actually have some operators which actually should be implemented possibly in the state. So therefore, let's create actually a solving class which actually solves the puzzle. So let's write a puzzle class, and the puzzle class will actually create a puzzle with the state and then actually solves the puzzle. So in that case, let's create a constructor for the puzzle, which is actually then you read the file and then construct the puzzle and solve the puzzle. So let's create a constructor, which again takes the file name as input, and then which then tries to solve the puzzle. So it's actually creates an initial state, and then you can do, let's say, a solve, or let's say, method, which actually returns a solution as a state. So which actually returns a solution state. So where we will also store, let's say, the initial state. So the initial state will be read with the puzzle, and then when we call actually the solve, then the solution is constructed with the help from the Q data structure. So in the Q data structure, we also need to modify, in that case, each element will not contain actually an integer, it will contain actually a state. So in that case, we should also modify standard state. So a standard element, so it will have a setter like this, or constructor. And then in the Q, as you see, we don't need to actually modify anything at all. So we have then have an queue of actually states. So other than that, we need to have actually possible extensions of the state. What do we mean possible extensions of the state? So the idea is, so how will we solve the puzzle? So if we remember actually the solution to the Dart problem, so in that case, let me share the solution. So in that case, remember that in the Dart game, we have this kind of solution, which we will write actually the solution in the solve part. And then here we have actually an initial Q, and then we actually enqueue the initial solution. And then we dequeue one element from the queue, and then if we have a solution, then we return the solution. So in that case, we need to have actually a check for solution in the state. So in that case, let's write a method for is a solution method. So which will return actually if the state is actually a valid solution. So if it is a valid solution, the function will return true. If it is not, it will return false. So actually, in that case, we can do something like a number of tents we have placed. That's actually a possibility, since we place a tent in each grid, or another one is actually we can just check every time. So to do things faster, let's write something like tent count, and then we will check the tent count with the tree count. So in that case, let's also write a tree count, which actually will count the number of trees or not. If the tents are equal to the number of trees or not. So in that case, we can easily write the function So if the 10th count is equal to the 3 count, so in that case, it is actually a solution. Okay, so then the number of 10s in the solution will be represented by the 10th count. The number of 3s in the solution will be counted as 3 count, and this 3 count will be actually settled when we read the state. The number of 10s changes according to each update. So therefore, we need to also have an update for the state. So then we can, for example, write a function which will return actually an array of states, which actually then returns the number of possible, let's say, positions to put a 10th. So for that reason, we can write, let's say, a state array. So in that case, the state array will, we will return a state array which will construct candidates, something like that, which will return us the possible next states from a given state. So in that case, we have a state, and then with that state, we return possible candidates. So it's actually like this here. So if we have a possible states, then we actually need to construct those states. So let me stop this share and then share actually the code to show you the state now. So we have a construct candidates, and which actually is return null, let's say, and then the construct candidates will return an array of states. So, but how will we decide to construct a candidate? So in that case, how will we do that? So in order to construct a candidate, we have, let's say, a given state, and at any state, we actually need to place some 10th to a current position. So if in the current position we can place a 10th, then that will be a possible candidate. If we don't place a 10th, then in that case, it will be, let's say, a good solution. So there are actually two possible alternatives for constructing a candidate. And we also need to know where to place actually a 10th. So in that case, we can solve this problem in many different ways. One possibility is actually to place a 10th in different positions for each tree. So in that case, we can, for example, represent it with actually a coordinate of the tree, so that we can see the next possible, let's say, 10ths to place. So there are possible alternatives to do, and let's concentrate on the 10th placement. So in that case, let's construct actually to do things a little bit faster. We construct a coordinate class. The coordinate class will have two members, which are the x coordinate, and which is actually another one, y coordinate. So these are actually, these will represent the coordinates of something, which can be a tree or a 10th. So let's put a coordinate here. So public integer x, integer y. So this x equals x, this y equals y. And then we need to have the getter and setters. So let's generate code automatically, which we only need actually the getter for x and y. So we have actually coordinates for x and y. And then what will we do? One possibility is actually having a coordinate array, which actually represents the coordinates of the trees, so that we can actually know where the trees are. And then we can also construct a coordinates of tenths, in that case, then we can, for example, check if any tenth is next to a 3 or not. So if we do in that way, then we can modify also the solution. So let's do also that. So coordinate tenths. So this will represents the position of the tenths where we have placed. So the number of tenth count will be actually for each tree. We will try to place a tenth to the next of the tree, and the number of possible placements will represent us a possible state. Okay, so when we construct a new state, then what we need to do is we'll construct a new state from a given state. So in that case, we will copy and paste, for example, the coordinates and trees, etc. So in that case, maybe we can actually remove the grid, which is also a possibility. So we can only check we only check for the coordinates. That's also a possibility. So let's, for this case, remove the grid actually. So this will be another possible alternatives. So then in that case, that's actually another alternative placement. Okay, so in that case, we are almost done. We construct the candidates and we solve in the puzzle, and we also need a main class which will actually solve the puzzle. So let's see a public static void main. And then we have string args. So that's actually a main method. Okay, that's actually all for the puzzle. We are finished here.